But they're putting the foreign antigen out on the outside of their cell membrane so they can show it to what? Other cells. Like they can show it to T helper cells and show it to B cells. Okay? And they can say, this is the what? This is the bad guy. And they can also see, are there any B cells that might match up with it? So that's why the macrophages and neutrophils, they're sometimes known as, they're sometimes called antigen, and I think I have this somewhere in your handout, antigen presenting cells, which means they what? They not only phagocytize the antigen, they also present it. They put part of it out on their surface to show it to other cells. Now, does that make sense? Remember, if we're going to make an army to destroy this, does the correct cell have to recognize it? And do the T helper cells have to recognize it? Yeah, and then we can activate an army. It would be like making a whole, like if you watch Lord of the Rings, they made all those orcs or whatever, those super handsome dudes. You know, they made millions of those orcs. Okay, we want to make millions of the white blood cells that are going to kill this thing. Okay? Now, does that take energy? Does your immune system require a lot of energy to do all this rapid cell division? Yes, that takes tons of energy. Okay? All right, now let's go back and let's just look at the picture. So in the top step, there's a big giant macrophage. Everybody see that? The macrophage is engulfed. It looks like a whole bunch of little bacteria. We'll just call it bacteria. So it ate a whole bunch of foreign antigens. And then the T helper cells are floating around in there, but they haven't seen it yet. See, there's an unsensitized T helper cell. And then there's a bunch of neutrophil, or I see a couple of neutrophils, and some of them are engulfing them and putting them out on their surface. And then some of the B cells, the correct B cell form like this one, has already done what? I'm going to erase all this other stuff. The B cell has what? Can you see what it's done? One of the pieces of a foreign antigen has stuck to those B cells. Do you see that? Want to show that in the picture? Don't I have like a little choke thing in here? Let's say here's the little foreign antigen stuck in there. Now, this B cell has been what? Sensitized. It's recognized the foreign antigen. Now remember, if this foreign antigen is sticking to that receptor, that binding site, is this the correct clone? It is. All of the antibodies it makes will have those same binding sites. It is the correct one. Well, I kind of think of it as that B cell is kind of like, oh, this is the thing I meant to destroy, all right, but can it destroy it yet? No, it has to wait to get what? The T helper cell has to activate it. It can't just divide on its own. Now, why do you think our body has that, like, backup system? We wouldn't want to accidentally activate the wrong B cell because it takes so much what? Energy. So much energy. We do not want to activate them unless it's absolutely necessary. Okay? And I've described it this way before in some of my other classes, but it's almost like if you've ever watched one of those shows where they're going to launch a nuclear warhead and they have to have two people and they both have to put the key in the thing at the same time and turn it. Have you ever seen one like that? Like there's the regular key and there's the backup key. And they both have to turn it at the same time. They don't want to launch the nuclear warhead unless the one person gives the command and then the other guy has the launch codes. Okay, it's to make sure that you don't launch the nuclear warhead if you shouldn't. It's kind of the same thing here. This thing, if all was really fast, this would be able to activate itself and be able to self-activate, but we probably have times when that would divide when it shouldn't and make an army when it shouldn't. It takes too much energy. So that's why we have a backup system. The T helper cell that has been sensitized to the same antigen has to activate it. Okay?
So, does HIV then connect the B cells or the helper cells that prevent?
No, HIV attacks the T helper cell.
Which prevents
and that doesn't prevent, the reason that prevents this from happening is when it attacks the T helper cells, it eventually destroys them, and our numbers of T helper cells in a person with AIDS is super, super low. They might have a few T helper cells, but the amount is so low because they've been destroyed by the virus that there's not enough of them in the body to activate the B cells. In a person with HIV, everything else is working fine. There's all kinds of B cells. Their skin is okay, usually, at first. Their immune system is fine. They got macrophages. They have neutrophils. They just don't have enough what? T cells, because the virus has destroyed them. Okay, and that's why you can be HIV positive, but still not have AIDS until your T cell count is low enough. Because you can be HIV positive and still at first have lots of T helper cells. It's not until most of your T helper cells have been destroyed that then you are considered to have AIDS. Okay? And when your T helper cells get really low, that's when you start getting prone to infections by things. Because you just can't do what we're talking about here. Okay? So now, follow the next step down. That sensitized B cell I have looping down the right side. Now let's go over to step 2. The macrophage and the neutrophil are showing the foreign antigen to what? T helper cells. And then in step 3, what's the T helper cell doing? The sensitized T cell. See, it has a star. It is dividing. You see that? It actually self-stimulates. Once it's been presented with an antigen, it stimulates itself to what? Divide. Now, here's the cool thing. If I'm a sensitized T helper cell, all of my offspring that I create when I divide by mitosis are also what? Sensitized to that same foreign antigen. So it's kind of like I'm sensitized, I know what the thing is, I divide myself many times, and all of my offspring are also know what the foreign antigen is. And then we make a whole bunch of those T helper cells. Now, can a person with AIDS do that step? No, they just don't have enough T helper cells to activate any of them. Okay? And if they are activated, it might even be an infected one, and it might not be able to divide. So they just can't do step 3 or step 4. So step 4 then, some of those sensitized T helper cells, they stimulate the correct clone that's also sensitized. See how the B and the T helper cell are both sensitized. The T helper cell stimulates the B cell with a hormone, and then the B cell divides many, many times. That's why I put all those little arrows there. And some of the cells, I put one of them is a memory cell, but most of them are plasma cells. You might want to write that there. The one to the left, it says B-mem, that's a memory cell, and the other one has P's on them. And all those little Y's are what? Are they spiders or centipedes or antibodies?
Antibodies.
They're antibodies. Now, where do they go? The antibodies go into the fluids of your body, and what's their job? Remember, they go where the fluids are. So blood plasma, interstitial fluid, can they go from the blood into the interstitial fluid and back into the blood again? Yep, and they're going to just drift. Remember, they don't have brains. They don't have a propeller. They have receptor sites, but they're just what? They're drifting in the water currents of your body, but if there is a foreign antigen there, they will what? If they bump into it, they will stick to it. All right? And so, if there are foreign antigens in your body, these circulating antibodies, I'll draw blue, will, or purple I guess, they'll stick to it. And so can you get big piles or clumps of foreign antigens held together by a whole bunch of antibodies? Is that possible to do this, to clump them all together? Yes. All right, and if you clump them all together with the antibodies, is it easier to engulf 1,000 antigens if you're a macrophage or one at a time? It can be held together in a big clump by antibodies. They can get eaten easier. And remember, the antibodies attract what chemical?
Complement.
Complement, which punches holes in them and kills them. The antibodies also stimulate inflammation. Okay? They also can bind to like receptor sites on toxins and stuff. That's how they work. Like, if you ever heard of an antitoxin or an antivenom, it's just antibodies that stick to the binding of the receptor sites on the toxin. There's all kinds of good things that the antibodies can do. They make them more noticeable too. They like flag them. It's like flagging the antigens so that the macrophages and neutrophils can see them easier, can get to them easier, it's inflamed, boom, they eat them up. Okay, so are antibodies good or bad?
Good.
They're good. All right, now let's go. Does anybody have questions about the picture? If you can explain that picture, then you can do it. Okay, that'll be the essay. Now, go to the previous page. Remember the